Today we have with us the Physics Nobel laureate and a professor at University of Waterloo, Dr. Donna Strickland. Hello.
Hello.
How are you doing?
I'm doing fine. How are you?
I'm good as well. Thank you. Firstly, what would you like to be called, Dr. Strickland or Professor Strickland?
Anything, I'm fine.
All right, then should I roll with Dr. Strickland?
You can call me Donna if you want.
Oh, okay. Then Donna. Okay, fine. So Donna, what drew you to physics?
What drew me to physics? That's what I was good at school. You know, I was really good at math and physics. And physics just sort of won out for various reasons, but it wasn't a hard and fast thing. But and then just looking from high school going into university, one of the things that caught my eye in a university calendar was a laser and electro-optics section of this engineering physics program. And so I just, to me, that was just a gut reaction. That just sounded a lot of fun to me.
Mm-hmm. That is very interesting. So would you say that physics is a natural talent, or that with the right guidance, like anybody can do it?
Well, we're changing around how we teach physics because it is one of the hardest ones, it seems, to teach. They're realizing that, of course, it's one of the subjects that is not following your own intuition, right? And so this is why it's a little tricky, and that when people first start learning it, it's very hard, because I think we're our best scientific selves when we're very young. That's when we're really learning, right?
Yeah.
And you teach yourself to crawl, and you know that you have to keep pushing yourself. So from the very earliest age that you could possibly remember, you've taught yourself that to keep moving, you must keep pushing. And this, of course, is not physics. Physics, you know, Newton let us know that if there's nothing pushing you, you will keep going at the same speed. And so, of course, we don't sense all the friction forces and all these other things that are on us. So this is why when we go to solve a problem, and I think in any subject, we probably would use our own gut reaction. I chose to do it, as I told you, just because of my own gut reaction. And so you have to reteach yourself to fight that and just use the physics principles, you know, the intellectual part of it, not your own gut reaction. Whereas most education starts from birth and keeps on going. And so I think it's this disconnect that gives physics this bad name. But you know, I think with new ways of teaching and using the peer-to-peer learning and saying that it's a questioning always, I think we could switch it around. And so then I think the difference has been those of us who could just let go our gut reaction and just, you know, see it, you know, analytically, we could get by that.
So according to you, primarily teaching physics is more like teaching a student to just let go of their intuition and think analytically about everything.
That's right. I mean, physics is one of the ones you really have to struggle with because you are reteaching yourself, right? I mean, it is almost that you have to reprogram your brain. And the other, I think, problem people have is that when your teacher explains it to you, you know, it follows from step one and it all makes sense. And then you try the problem yourself and you're back going, well, now this isn't making sense anymore, right?
Yeah.
And so you really do have to try the problems yourself. So again, maybe I'm always someone who liked to do puzzles and stuff. And so math and physics to me was just another puzzle. And so if it didn't work, if you could just say, oh, it's a puzzle, let me figure it out like a game, then that's the type of person who probably also liked doing it. But yeah, you do have to sort of, I think, rewire your brain to think that way. Mm-hmm. And that it takes that effort.
Yeah, I agree. That is a very interesting perspective to me, honestly, because I never thought about physics and maths in this manner. But mm-hmm. yeah, I agree that when I look at physics, it's very counterintuitive for me. So, you know, you were saying that you like puzzles and you sort of, you know, you rewired your brain, or, you know, is there someone you would owe your talent to, or someone who helped hone your talent?
Well, I mean, part of it is genes, right? I mean, my dad was an electrical engineer and had been a chemist, and my mother was very good at math, right? She should have gone into math, but she fell into the trap in the 50s, well, I guess 40s. She went to the university in the 40s, which was amazing that a woman from a small farming town in rural Canada even went to university, mm-hmm. But was convinced she shouldn't go into math because she was a woman. And so I have that talent anyway. So I mean, I probably have the type of brain that was willing to do this. Yeah, other than that, I can't tell you. I mean, I had some great teachers all the way through school too. So.
Okay. So I know that you work on pulsed lasers actually. Could you tell us a little bit about what you're working on currently, like in layman's terms, because I honestly won't get the complexity of things.
Well, the idea is that I work on short pulse lasers.
Okay.
And so again, there's this idea of, how do you see something that's happening very fast? And so quite often when we give these talks about why do short pulse stuff, we'll show this horse racing thing that happened, 150 years ago. And there was a controversy that all four legs come up off the ground at the same time. And people watched it, and some people said, yes, I see it. And other people say, no, I don't see it. And so they figured out, Meyerabridge figured out how to set up a series of cameras that would time it such that they could watch the horse in different places, and that the shutter speed was fast enough to stop the motion of a horse. But a horse is a very heavy thing. Yeah. And so it can only move so quickly. So that millisecond time scale, was fast enough. But then along came Edgerton and he said, okay, forget mechanical speed because mass can only move so fast. And he came up with just the electronic flash. So now if you have a dark room and the only light is there that was microseconds. Now, there's lots of pictures on the web, but one of the famous ones, and the one I use, is a stopped bullet, right? It's gone through an apple and stopped. And so you could stop that action. Now we're getting to the point where we can actually maybe stop the action of atoms and electrons. So that's fine, except now an atom is so small, or a molecule is so small, you can't just image it with a camera. Yeah. And so we use these nonlinear techniques, and that means we also need a lot of peak power in our lasers because we use the ionization. And if you can imagine, we have two atoms making up a molecule. If we want to watch the motion, it's really what we're watching is how far apart are these two atoms. Mm-hmm. The way to do that, or one way, is if you could just instantly take charges off each one. Okay. Now you have what we call the Coulomb force. There's a charge and a charge, and that's one of the fundamental forces. Only they're very close together. We do these experiments. If you go and see it, you'll rub rubber with, fur or something, and you put charges on these little pith balls, and we watch them separate. But they're a millimeter apart, and the force goes with the distance squared. Now you're only an angstrom apart. Boom! We call it Coulomb explosion spectroscopy. And how, that energy, the Coulomb energy, turns into kinetic energy, and we measure that kinetic energy. So that's the idea of what we're going for, is that we want both intensity and we want short pulse, because if this thing is wiggling, very fast, there's no point in taking the whole time to take it off, because you would just get the blur, right? It's the same idea, you would just get the blur. So you want to stop it here, want to stop it here, want to stop it here, right? So that's the goal of one of the goals anyway. Oh, wow. That's that sounds amazing to me. Honestly, that is something I might want to go into in the future, honestly, because I really like physics. Okay, so what was the most exciting discovery you made in your career so far? I don't know. It might depend on what we're working on right now. Again, it's just a puzzle. We were trying to make these very short pulses, and to get very short pulses, you actually need a lot of colors. And it's the way the colors add up where they, all add up together, because color is just different wavelengths. Mm-hmm. And so you take all the different wavelengths and time them up here. Well, then eventually, as you go away from there where they're all peaking, some of them are troughing while others are peaking, and that's how you cut the power out. So that's how we make short pulses, is we have a lot of colors and put them all together at one time. So the question is, can you get more colors? And so we were using this nonlinear thing, and we were getting this, what I call a picket fence of frequencies, like we thought we should. Huh. And there's all these other ones now in between, and we don't even know why they're there. And so that's what I'm working on now. And I just think, it may not be useful at all to find out, but I just like to find, so my students and I are trying to find that out right now. So I like that one. So you've got yourself a new puzzle to solve. That's right. Okay, amazing. So what's a topic in physics that you never get bored of? A topic I never get bored of? Yeah. Well, obviously I've been working on short pulse lasers for 30 some years, so I never get tired of that, right? I'm still always trying to find a new way of doing it or something. So you know, I don't get bored that easily, I don't think.
I almost guessed it. I was like, yeah, she is going to say short pulse lasers. So, okay, then how do you, I mean, of course, you know, you're a scientist, and in research, you know, 99 things don't work, just one works. So how do you deal with all this failure in your research and your projects?
That's right. Patience is one of the things you need. I mean, not only do you need the creativity to keep thinking about, well, how do I try it differently so I can, you know, but you also need the patience and know, you know, okay, just let that go. I have come close to kicking my laser sometimes. I never have. But I usually go out for a walk. I love to walk. I just like, you know, especially if you can get out in the woods or something, I just think that's just clears your mind. I must be the only person. I don't walk a dog, and I don't put something in my ears. I just go out and let nature amuse me. So that, I find that very calming.
Okay, so that is like, so would you have any advice for us who like fail every day and who would like to deal with failure, except for the walk?
Well, I think you have to accept that failure is just part of it. This is one of the other disconnects with the way we teach physics, or probably teach anything, but or any area of science, is that while we're teaching what's already known, and then we test you, do you know what's already known? But doing science is using that information, but always asking why, right? I mean, if we already knew the answer, we wouldn't have to do the experiment or the theory or whatever, it would be known. And so going out there and not really knowing means that, you know, you can spread out the path quite wide, and it's hard to figure out the correct one that will give you the answer. So yeah, you have to understand that we don't know what we're doing, but we have a good background as to make really intelligent guesses, right? And again, I also like to say that physics is still a team sport. You may think it's just you by yourself working, but you will get stopped. I mean, there's, you know, maybe Einstein, but Einstein probably talked to a lot of people. I think that you have to have the conversations. This is what works so well between a supervisor and a student, right? The student does not know as much as the supervisor at the beginning, but understanding the project they're working on is this conversation, right? And then you take it out to the whole group. Maybe somebody who's working on something on the side would have a good insight. You go to conferences and you talk to these other people that are in the field, but not doing exactly what you're doing. It's got to be a team sport, and you've got to all sort of talk it through to see if somebody else has seen something too that looked like that, and helps you out.
Yeah, well, I mean, yes, that is solid advice. Should do that.
You know, we're so worried about honesty and intellectual whatever, but you shouldn't do assignments by yourself. You should write them down by yourself. Like when you finish with the conversation, don't be copying anybody else's. You have to finally do the assignment yourself, because as I said, you have to have worked it through in your own brain.
Yes.
But I think it still comes from having a conversation. And this is the way we're talking about peer-to-peer learning too, is that it is these conversations that really pushes your understanding of how science works, right? And can help you push through that boundary of when nobody knows, but you at least have the right tools to get.
I think that talking to people will probably, you know, help you utilize, and it'll basically help you reach that common goal, honestly, and help you understand things from their perspective. They have their own creativity. Everybody is a creative person. So I think that, at times others' ideas can actually help you a lot in the long way.
Well, and you having to also have the conversation to help explain your idea to them really helps it crystallize in your head while you're teaching it. So it's a combination. And so it's the teacher and the teachee, I don't know, the learner and the teacher are one and the same, and you go back and forth.
So I know that you're a professor at the University of Waterloo. Is there something that you've learned from your students in all your years of teaching?
Oh, well, sure, absolutely. You know, I mean, it's the students, like my grad students are certainly the ones in the lab doing it, right? And so it was my grad student, you know, these extra lines just said, what is this, Donna? Look at this, we've got to study this, right? It was his idea to study that. And different students bring in different, I would like to try it this way, you know, they saw so-and-so, I do, you know, go for it. If we have the equipment, or, you know, if it's within our realm of being able to do it. So yes, I do expect certainly by the end of your grad career, you should be teaching the faculty member something. Right? That's the way it goes.
That should be the dream.
But I mean, and there's always the undergrads too that are just so mind-blowingly smart that it's always a pleasure to have conversations with them and see how they're coming at it from a whole different perspective.
I think, yeah, science is all about perspectives and solving that problem together. And, you know, you really, you helped me understand this perspective, honestly. I never looked at science being a team sport. I thought it was like, you know, you just sit in one corner and you keep dwelling on one problem. And
no, you won't get anywhere that way. No.
And you hit that Eureka moment.
Right. No.
So have you had any like Eureka moments?
Sure. What I like to talk about was when I was a postdoc, actually. And we were working on the connection between something called continuum generation. Okay. And this is one of the things I love to show high school students. I'm trying to get a first-year undergrad lab on it. If you take just a glass of water, like just a water cell.
Okay.
But it can be anything clear. It could be a piece of clear plastic and a piece of glass, but just water. And you take our short pulse laser in, it'll be a single color in the infrared. You can't even see it. It's just in the near infrared, just past where your eye sees, past red. And it goes into the water and all of a sudden becomes every color of the rainbow. It is so gorgeous to see. Just it's like magic, right?
Yeah.
And when I was a grad student, people were using this because we had short pulse lasers in the red, but nowhere else. Well, what if you wanted to do something but required a different color? Well, now you just put it through, and we were actually putting them through jets of ethylene glycol, which is a sort of a viscous kind of clear liquid. So very thin jet, and in would go the red and out would come every single color. And it had still the same short time duration. So now you could pick whichever color you want and have this short pulse. So that was cool. So then when I went on with my postdoc with Paul Corkum, we were working on understanding where this came from. And he had noticed with his previous postdoc that it was coming at the same time as self-focusing, which is this different nonlinear thing, where if you think your light is going through, if it's powerful enough, you all of a sudden find, because a laser beam has more intensity in the center than the edges, there's a nonlinear thing that makes that refractive index, the thing that makes light go slower in glass than air, changes with intensity, if intensity is high enough, and actually self-focused, because the center would start traveling slower than the edges, and so then it focused in. So we noticed these two things were happening at the same time, and we sort of put it together when I was working with Paul, and I just found that project really interesting and fun to do.
Honestly, hearing you talk about it, it's a Eureka moment enough for me. I would love to see it someday. So in what ways did winning a Nobel Prize change your life, if it did?
So many ways. Yes, I mean, I did this work, 35 years ago. And I was really well known around the world in the high intensity laser community because I did this work. But it's funny that when you're given the Nobel, all of a sudden people like yourself, all of a sudden think that I'm this important person and worth listening to. And so it's a very strange thing that you went through very, subdued life for 30, all these years. And then all of a sudden people think, whoa, we have to talk to her because, she must have something to say. And so, first of all, it can go to your head, but second of all, it also puts this pressure on you to not say stupid things, which I usually do, and how to what to do, but also then just to handle the schedule.
Yeah.
This is the first year that we have multiple living female physics laureates. So when Andrea Ghez won this year, I sent her an email saying, I've just formed a new club called the Female Physics Nobel Laureate Club. Would you like to join? Which she joined, right? And I said, it's the only time we've ever been able to have such a club. And then I did, because other Nobel laureates had reached out to me, if you have any questions about how to do it, contact me. My fellow Canadian Art McDonald was very good about that, but there were others as well. So I said, if I can help in any way. And her first question back to me was, how do you handle all the requests, And she works in something that was, black hole. And I think she was already thinking that she was having a lot of media requests and a lot of, and yet it's just this whole extra level, right? Yeah. And so, you know, obviously we have to say no most of the time. And that's a very strange thing when you just, the requests just keep coming and you can't say yes to everything. And then, of course, I've gotten to meet incredible human beings. I've had an audience with the Pope. I'm not Roman Catholic, but that doesn't, you know, he's just like,
Yeah.
he's quite a person, right? And I've met Apollo astronauts who have landed on the moon. And I've met Brian May of Queen, for goodness sakes. So, you know, it's like, how do these things happen? But they do, because you're sort of thrust into this other kind of world that a regular scientist working in her lab doesn't even know is out there.
Okay, firstly, I would like to thank you for accepting our invitation for interviewing you. Thank you so much. I really, really appreciate it.
Well, of course, it's made it a little bit easier without the travel. But I can tell you now that we've pushed so much of 2020 to 2021 is that there's nothing left in 2021. I mean, I'm just in the air going here, there, and everywhere.
Okay. So what do you enjoy doing in your free time?
Other than walking.
Yeah.
I don't know. I watch TV. You know, my husband and I are rewatching this old British mystery detective show called Morse, and it's on at lunchtime here now. So we have our lunch watching Morse. We quite like it. He's just the curmudgeonly old guy that's out there being a detective. What else do I like? Oh, well, I love just going to my cottage in the summer and just floating on the lake. So we have the Great Lakes here in Ontario, and I have a cottage right on one of them. My sister is nearby and my brother's nearby, and we just go there for the summer and just chill out. We love that.
Sounds like quite a vacation. Honestly, my next question for you was like, what's your TV show or favorite TV show or movie and why? But you just answered that, didn't you?
Yeah, I do like mysteries, and yeah.
I love mysteries as well. Do you read mysteries?
Yes, I do.
Who's your favorite author?
Well, that's a different thing, because, you know, I will tell you, I've answered this question a lot, and you know, my favorite book is Pride and Prejudice, which is not a mystery. So I like those sort of old classical English things. But do you know, the one that was made me sad is I got through the whole detective thing. I remember anybody's name, but it was a whole series of A is for this, B is for this, C is for this. Oh, I'll think of her name. But anyways, and she got right to, she died just before Z. Or
Sue
Z.
Grafton. Sue Grafton?
Yeah, that's it. Sue Grafton. Loved hers. So I got all the way through that whole series. So I was ready for the last one. Yeah.
Yeah, I understand. That was really heartbreaking that she died just before the Z one.
That's right.
Did you or do you help your children with their physics assignments or homeworks?
My daughter won't want me answering this. My daughter's in grad school in astrophysics now. So obviously I can't help now. I tried to read her paper that just came out, and it's not possible. But I did probably in first year physics. I remember teaching second year physics when she was in second year, and I'm thinking, oh, Hannah's learning the same thing I'm teaching now. But yeah, first year physics, I probably did help her more than most people would get help with. And it was funny, she was home for Thanksgiving, and I heard, I shouldn't tell you these stories. She was helping her friend over Skype or something, or FaceTime, I don't know what she was using, doesn't matter. And I heard him saying, wow, I can't believe you figured that out on your own. That's amazing. And I knew I had helped her with that. I was like going, Hannah, are you going to let him think that you figured that out on your own? And she goes, oh, do you think I should say that you helped me? I kind of think you should, Hannah. I mean, no point letting him think that, So, but yeah, I helped, because I also taught first year physics. So when she was in first year physics.
It must be quite a perk having like a Nobel laureate in physics at home, just for help.
Of course, I wasn't the Nobel laureate then. So trust me, my kids didn't think I was anything too special either, but she did know that I taught first year physics. So she did appreciate that she was the only one in the class that had a physics professor for a parent at home.
Yeah, quite some help, honestly. A lot of us need help.
Exactly.
Okay, finally, do you have any advice for those of us who want to pursue physics much like you did, especially for young girls?
Well, I think if you want to do it, you should try it. And, and I never I was one of the very few girls, but I never felt like I didn't belong. I knew in my heart and soul that I was good at math and physics, and that's where I belonged. right? And so I knew that I was good at it and a girl, and therefore girls could do physics. So at no time, and it didn't matter what anybody else said to me, they were wrong about it. I was just they were wrong. And so, you know, I didn't suffer all these other problems that some people feel. That doesn't mean I didn't have insecurities, right? I remember being in a class that they said they separated based on our marks from high school into like the top. There was, you know, 20 physics classes, and 2 of them were just for the top students. And I went, how do I compare? And again, that was my mother who was keeping me grounded. She would say when I went to university, just because you're really good in high school, don't think you'll be really good at university. All kinds of good students go, and they don't necessarily make it. So, you know, I had my mother who, you know, would lift me up and tell me I could do anything, but also kept me grounded. Like, don't think you're so super special. And so, you know, you would have those anxieties, but I also think girls and women should realize that the difference is not our level of confidence compared to the boys. The boys are taught to have bravado. They will show off their confidence.
Yeah.
And girls are not taught to do that. But that doesn't mean, I don't really think that we are less confident than the guys. The guys just have to steamroll through it by showing off, right? So you don't want to get stopped in that trap that they're so confident and you're so not. And so ooh, maybe I can't do it. No, trust everybody that everybody is kind of thinking maybe they can't do it, right? And even the people at the very top think that, because no one's really, you know, comparing themselves to the bottom. Everybody's always comparing themselves to either, you know, even if you don't even think your fellow students are keeping up, maybe you're thinking, how do you get to be the professor who knows so much? It doesn't matter where you are. There always seems to be people that seem to catch it faster or know it better or retain it more or whatever it is, right? So you just have to have belief in yourself and then go on with that.
Okay, thank you so much. That was really, really inspiring for me, because, you know, in my high school classes, I see all these guys, and like in science, especially maths, physics, all these guys, and I'm honestly one of the few girls who's doing well in physics and maths. And I don't know, I just needed to hear that, that yes, everybody has insecurities.
Yes.
So that concludes our interview. Thank you so much for all the time and your inspiring, fun words.
Thanks for having me.
I really had a great time.
I enjoyed it. So good luck with your career.
Thank you so much.
We'll
Bye-bye. Take care.
Bye-bye.